Hello, dear students. Today we have the last prop of Book 3, Proposition 37 of Book 3. Then we go on to Book 4. If there be a circle and a point taken outside the circle and two lines be dropped to the circle, one of them cutting it and the other one you don't know, it's either cuts it or touches it, but you just say it falls on it. But you also know one other thing, that the straight line which cuts the circle, the rectangle contained by that whole straight line and the other part being the line between the point outside the circle and the point on the convex of the circumference where the line cuts the circle. If that rectangle contained by the whole and that part is equal to the square on the line falling on the circle, that line which falls on the circle will be actually touching it and not cutting it. Okay? So here's our given circle, point outside the circle, two lines coming in contact with the circle. One of them, it's given that it cuts it, and the other one, you just know that it falls on it. You need to prove that it's only touching it and it's not cutting it. That's the whole point of this prop, showing that this line touches the circle and not cuts it. It's given that it comes into contact with it, that is to say, it falls on it. Okay, but it's also given that this rectangle made by this and this is equal to the square on the line falling on the circle up to the point of contact. So the rectangle contained by the whole of the cutting line and the part of that cutting line, which is between the point of contact and the point where that line cuts the convex of the circumference. This is the concave, convex of the circumference. That rectangle, if that's equal to that square, the square on that, then this line definitely touches the circle. Let's set out to prove that. Okay? We're going to connect some lines here. Okay? We're going to connect this point of the center with the point of contact. We're going to connect the point outside the circle with the center. And then we're going to drop a line from the point outside the circle, a line touching the circle. We know we can do that from previous prop. Given a circle and a point outside the circle, to drop a line touching the circle. Somewhere around there, say, touches it there, say. Okay? I know it actually looks like it cuts it, but I'm not a very good artist, so let it touch it. Okay, right there. All right, now let's connect this point of touching here. Okay? So let's see what we got. We know because a straight line has been dropped from the center to the point of contact of the line touching the circle, we've proven in the past that that line which so touches the circle and that radii, if this were extended, that diameter, is a right angle. So this is right, okay? We also know that because these are radii of the circle, that they're equal to each other. We also know that these two triangles have this in common, so it's equal to itself, okay? So, and we also know one other cool thing, that because a straight line has been dropped on the circle, touching the circle, and another straight line, let's go it this way. Well, let's just extend this thing out. Okay. And another straight line has been dropped, cutting the circle, that the rectangle contained by this and this will be equal to the square on this, okay? But it was given, I gotta show, but also the rectangle contained by this and this is equal to the square on this. Just remember that, because you have a straight line cutting the circle, not through the center, etc. Okay? But let's focus on the one to the center. So whatever is true about this thing will be true about this thing. Okay? So here you have a straight line where you have this and this, the rectangle contained by that, is equal to the square on this. But because it was given that the rectangle contained by this and this is equal to the square on this, and the rectangle contained by this and this is equal to the rectangle contained by this and this, because they're both equal to the square on that, so they're equal to each other, it must be the case that the rectangle contained by this and this, it being both equal to the square on this and the square on this, that the square on this and the square on this are equal. Two things equal the same thing are equal to each other. Therefore, the two lines are equal, okay? So here we have two triangles, okay? And we have side, sorry, let's do it this way. Side, side, equal to side and side. And the base equal to the base. Therefore, the angles will be equal to the angles, okay? So, namely those which subtend to equal sides. Well, this one is equal, okay? So, this angles which it subtends are equal. So, this angle being right and being equal to this angle is also right, okay? So, now you have a line from the center touching, coming in the, making an angle at right angles to another line at the end of the diameter. We proved that in the past. So if you have a circle and a diameter, and you take a line out, and you, at right angles, that line necessarily touches the circle and doesn't cut it. We've proven that in the past. So this line is necessarily touching the circle, which is what we set out to prove. Okay? So then if that line, that original line falls to the center of the prop's even easier to show. I just want to make one thing sure, make sure of one thing. So it was given that the rectangle contained by this and this is equal to the square on this. But here's a point outside, and this is touching the circle. So it's necessary, and this is cutting the circle. So it's necessarily the case that the rectangle contained by this and this is also equal to the square on this, okay? So here you have the rectangle contained by this and this equal to the square on this, and the rectangle contained by this and this equal to the square on this. So these two guys are equal to each other. Okay, then you do the side, side with the, and side. Okay, so I think I messed up. I'm not sure, but I have to review this video. I think what I said earlier was true, but now I know what I just said is true, because the rectangle contained by this and this is equal to the square on this, and the rectangle contained by this, that was given, and the rectangle contained by this and this is equal to the square on this, because from the point of contact, you've got a line cutting the circle and a line touching the circle. We've proven that in the previous prop then, that the cutting line, the rectangle contained by the cutting line, namely the hole and the part between the convex and the circumference on the outside, is equal to the square on the one touching it, okay? So this square is equal to this square. Great. And therefore the line is equal to the line, and then you can do side, side, side. So I added an extra step. I don't know if it's true. I got to review the video. Seems like it would be, that the rectangle contained by this and this is equal to the rectangle contained by this and this. That's kind of blowing my mind, because as this thing moves along, it's all, the rectangles that they make are always going to be equal. That is to say, with the hole and the part between the convex and the circumference and the point outside will be always equal to the rectangle contained by the hole and the part between the convex and the circumference on the outside, no matter where you move that thing. Okay, so we'll see if that's true. I have to go. So that's it for today, chicos. We're going to do together the other prop today, and you'll have this for Monday. Thank you. Bye.